Welcome to AP Calculus AB video for skill number 116. I can translate key features of trigonometric functions between equations and graphs and use this to describe transformations. Alright, and the trivia question for this lesson, we've learned that the top step upon which the temple sits is called the stylobate, and that the lower steps are called the stereobate. But what is the sum of all of the steps called? The pedestal upon which the temple sits. Alright, so we'll start our notes on page 116A. And skills that we should have take over from pre-calculus is we should really know these functions cold and what they graph like. The first function is y equals sine of x. And if we have our axes, our horizontal axes and our vertical axes, the function starts at the origin and it does a wave, and really this keeps going forever in both directions, so I just drew one period's worth. The period of that function, the amount of distance it covers to do one full cycle, is 2 pi over 1. So 2 pi over 1. And I phrase it that way because later on that number will change. But the parent function has a period of 2 pi over 1. It starts at the origin. It's an odd function. You can see that it has that symmetry around the origin. The next one that we should know cold is cosine x. This is also a sine function, or it's called a sinusoid, but the cosine function is also a wave, and it does keep going forever in both directions. The period of it is also 2 pi over 1. We just start at a point of 0, 1, and then we drop down and then back up. So it takes a distance of 0 to 2 pi radians to complete the full cycle. It should be noted that the points where it crosses the axis is at pi over 2 and 3 pi over 2, and that the minimum occurs at pi, or more specifically, that's for if it has a period of 2 pi. Compressed functions, those values will change. The next function, which is a little bit harder to remember how to graph, is y equals tangent of x. And for tangent x, if we have our axes labeled, we can call out 0 and then pi, 2 pi, 3 pi, and basically what we have is something which kind of resembles a cubic, though it's not exactly a cubic, that curves across at those key points. We get vertical asymptotes. At the values of pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. And this pattern repeats endlessly, so it also continues to curve and curve and curve. So unlike sine and cosine, the period for this function is going to be pi divided by 1. So if we have the graphs of sine, cosine, and tangent down, we could, in theory, generate the other three trig functions of cosecant, secant, and cotangent from those graphs. And to explain how we do that, we know what the graph of sine of x looks like. It starts at the origin and it goes up and then down. Well, cosecant is the reciprocal of that. So what I did is I graphed my sine curve and then I took the reciprocal, which means it's kind of hard to picture, but if you do sample numbers, like a height of 1, well, 1 divided by 1 is 1, so that's going to be the same. But if we do 1/2, a height of 1/2, if we go 1 divided by 1/2, we'll get a height of 2. Or if we do 1/10, it'll have a height of 10. So you may not understand the math behind it, but if you can picture drawing the sine curve and then drawing upside down u's or n's at each maximum or minimum, then you can have the cosecant curve. We wind up getting vertical asymptotes at pi and 2 pi and 3 pi and 4 pi and 5 pi because 1 divided by 0 is undefined, so it makes sense the graph doesn't touch there. We can do the same thing for secant. If we have the curve for cosine and we draw the curve for the cosine, when we wanted to draw secant, we can draw the curve for cosine and then we flip and do the same thing that we did for the above equation. We have these u's which come down and touch at the maximum of the curves or the minimum of the curves. So that's the secant function. I didn't graph the cotangent function, but if we wanted to graph the cotangent function, remember tangent does something like this. So if we're going to do cotangent, that's 1 divided by tangent. So 1 divided by 0 is undefined, so this is where we wind up getting our asymptote at every time it crosses. So every spot where tangent crosses, we're going to have a vertical asymptote for cotangent. And then we can say 1 divided by a really small number is a very large number, and it comes down and does something like that. So it's not too important to me that you're able to graph secant, cosecant, and cotangent, though you will find that it's pretty useful to understand these ones. Really the most important thing is to have an intuitive understanding of graphing sine and cosine. So I'm going to focus on graphing sine functions and transformations of sine functions in the next couple pages of the notes. You can actually use these same transformations for cosine or tangent. You just have to modify your graph. So I'll do some transformations on sine first, and then I'll give you an example of a cosine. So we learned that a vertical stretch of a function, we're multiplying a number by the function. So if we do the same thing, multiply a number by sine x, that's also a vertical stretch. And when our original sine function would go up to a height of 1, it's now going to go up to a height of a. So this kind of adjusts the amplitude of the wave. So when we write 2 sine x, we're going up to a height of 2, and then we continue down and drop to a low point of negative 2. So it's taken all those y values and doubled their size. Next we have a horizontal stretch, and if we say sine of 4x, the easiest way to understand that is, since our period is usually 2 pi, we're fitting 4 curves into that distance of 2 pi. So where we did go up and then down and then back to the original spot, we're going to fit 4 of them now into that distance. So the way that I did that was I cut it in half and then I cut it in half again. So I divided my distance into 4 equal spaces, and then I drew my sine curve between those 2 spaces. So up, down, up, hit the space. Up, down, up, hit the space. Up, down, up, hit the space, and then up, down, up, hit the space. If it were sine of 5x, we would want to divide it into 5 spots. So generally you can think of this number as defining how many times we can fit the curve between 0 and 2 pi. An alternative interpretation is saying that the period of your transformed function becomes 2 pi divided by 4, so your period is pi over 2. So our curve goes up, down between 0 and pi over 2, and then up, down between pi over 2 and pi, and then up, down between pi and 3 pi over 2, up, down, etc. This is a useful way to think of it, and sometimes some people prefer using this method for graphing. It's exceedingly useful if you have like odd numbers and it's kind of hard to divide your space easily by drawing. Alright, the next transformation is a vertical shift, and if we tack on a number at the end of the function, it shifts it up or down. Plus k means k units up, so if we write our function sine of x and then we change it to sine of x plus 2, that means what was our center line at 0 has now shifted up 2 units and become the new center line. And then the curve behaves the same way around that center line. Up, down, up over a distance of 2 pi, up, down, up over another distance of 2 pi, and it keeps repeating. Okay, so we can write a general sine function in this nasty form. F of x equals a times sine of 2 pi over b of x times c plus d. It's got a lot of messy numbers in there. And I think it's kind of easy if you start to dissect each piece. Like the x minus c is going to be your shift left and right. The plus d is your up-down shift. The a is your vertical stretch. And then this 2 pi over b is kind of the newish transformation. That's a little bit harder to understand. But let's tackle one with numbers in it. And I start pretty straightforward. I have 3 times sine of 2 times x minus 0 plus 5. So the first thing I think is, hey, I'm shifting up 5 units, so I'm going to take my graph, which I've drawn here, and I'm going to shift my horizontal line up 5 units. So now I know that the curve probably does something like that, about the 5 units. The next thing I notice is that there is an amplitude of 3, which means if I have an amplitude of 3, I can go at maximum 3 units above my horizontal or 3 units below my horizontal. So now I can be more accurate and say it goes up to the 5 plus 3 and then down to the 5 minus 3. And then it fits within that kind of bar that I've drawn. And I strongly encourage you to make a habit of drawing these 3 lines because they really will help you in drawing a nice clean graph. Finally, I have this number 2 to deal with. Actually, I have the horizontal shift, but there is no horizontal shift, so we know the start point is going to be on the vertical axis. And then we've got this piece that affects our period. So our period becomes, if we go 2 pi over 2, that is equal to pi, which means it takes from 0 to pi to create our full curve. So what I've done down here is I've drawn the curve fitting between my top and bottom line, and when I finish a full cycle, that's where I label pi. Alternatively, like we saw on the last page, we could have drawn 2 cycles over a distance of 2 pi. Alright, so our notes will finish on page 116E, and I walk us through drawing a transformed cosine function. And like before, the first thing I noticed was it shifted up 4 units. So I draw my horizontal line at 4 units up. Then I notice that the amplitude is 2. So I'm going to draw a horizontal line 2 above and 2 below my center line, and you can see that in the second drawing. Then it says there is a horizontal shift 2 units to the right, which means rather than starting on the axis, we're going to start 2 units over. So what I've done is drawn a point 2 units over, and I drew pi and 2 pi in there because that's useful, and 2 is roughly 2/3 of the distance of pi. And you'll notice that I put the point on the top line, and that's because the cosine curve starts at the top. And so it might look something like this, or maybe it's stretched out a little bit more and looks like that, or maybe it's really stretched out and it looks like that. We're going to deal with this stretch on the next step. So I've got the start point established. I've got my max and min lines in my center line. Now we're going to talk about the stretch. And it looks like what we have is a period of 2 pi over 3. And that's not an easy number to think of, so why don't we just think of it as 3 cycles over a distance of 2 pi. So if we start at 2 and we want to go a distance of 2 pi, we're going to eventually get to 2 pi plus 2. That would be our total distance. So between the red dot and the blue dot, we want to make 3 cycles, so that you could think of dividing it into thirds, like that. So we've got 3 sections, and we draw our curve. Here's one section, the second section, and then the third section. And that's what the curve looks like. And I've drawn it down below so we can take a look at it. There we go. A period of 2 pi over 3. 3 cycles over a 2 pi distance. That's the way I like to think of it. This 2 pi over 3 period is kind of difficult, so if you want to think of it this way, that's fine. And I'm sorry that the video was very long. There was a lot of graphical things to explain, and we'll probably spend a little bit more time than just one class discussing this and get lots of practice on it. As always, please let me know if you notice a mistake that I made. Extra credit is awarded to those who find and call me out on mistakes. Thanks for watching. Oh, the trivia question. Thanks for watching the video for Skill 116. And as I mentioned earlier, the top step is called the stylobate, and it sits atop the stereobate. The term for the full base of the temple is called the crepidoma.